Hi everyone, our project is HDFS emulation and our group members are Yu and Xin Zhang. Here is the architecture of our system. We first use Vue.js to implement the front-end UI interface, and we use Python plus Flask to connect our front-end page with our backend database. And our system can also accept shell commands which typed by users in the terminal, and we use socket to connect the shell interface with our backend database. And for the database, we use one name node and 4 data nodes to store the data. And for the actual design of that, let's directly look at my database. And in order to emulate the real file distributed system, in reality, data nodes are more likely to distribute across different clusters all over the world. We actually store our 4 data nodes in 4 different databases, and I have data node 1 and 2 on my machine, and my partner has the other 2 data nodes on her machine. So for the data node, the keys are the block number and the values are the actual data. And for name node, it has 2 main sections, directory section and inode section. Under directory section, the keys are the n number of each directory and the values are the contents under that directory. For example, for I1, it's a directory under I0. I0 stands for root directory, and under I1, it has a file called pre1.json. So use this directory section, we are able to explore our system's directory structure effectively. So for the inode section, the keys are also the I number of each directory or file. And for the directory, it records the name and type of that directory. For the file, it records more information, including the file's name, preferred block size, replication factor, size, type of the file. And for each file, it has a blocks section to record the block's location. So for the block section, the keys are the block number and the values are the data node number, which stores the actual block. And since our default replication factor is 2, each block has 2 replicas. And if the file size exceeds our predefined preferred block size, our system will divide the file into several blocks and record block information under this block section. So for this file, it has 2 blocks, B0 and B1. And for B0, one of its replicas stores in data node 2. So let's look at data node 2. It has the actual data. So that's basically how we design our name node and 4 data nodes in our database. Now let's look at the code to see how we implement that. So first, our system needs to create the name node and 4 data nodes. So we write a function called init name node and init data nodes to create these nodes, and we use put function to implement that. And for the name node, you also need to add a number section and directory section under the inode field, the name node field. And initially, the system only has root directory, so we assign 0 to a number of the root directory, and we add the metadata of the root directory to the number section and the directory section. We also design a function called write to name node to update metadata to name node. So when a user wants to put a new file or a new directory to our system will automatically call this function to update metadata. So basically, it just updates metadata in the 2 main sections, in the inode section and in the directory section. But before that, it needs to generate a new number for that new file or new directory. So the way we generate new number is we always want to find the last number of our system, and we +1 to generate the new number for that new file or that new directory. And then since the argument path is an absolute path, we need to split it to get the name and the parent directory of that new file or directory. Then we can write back data to another section. And if it's a file, the data looks like this, and if it's a directory, the data looks like this. And we also use put command to put the data into the iNumber section. And if it's a file, we also need to write the block's location under its block section. And for the directory section, if it's a directory, it needs to first write a new entry into the directory section, and then it can write iNumber and name under its parent directory. We also write a function called allocate blocks to allocate a name node to a block. So let's say a user wants to put a new file into our system, so the system will call this put function, and our system will divide the file into several blocks, and for each block, it will call this function to allocate a data node to store the block. So for this function, and in order for our system to balance the block storage, we always want to return the data node that has the minimum number of blocks. So to do that, we first record the number of blocks in each data node, and we find the minimum number of blocks in each data node. And if there is only one name node with minimum number of blocks, we just return the data node number. And if there are more than one data node with the same minimum number of blocks, we just randomly choose one named data node to return. That's basically how we design our database and how we implement that. And next, my partner will show how the user can interact with our system.
Okay, so the next part of our presentation would be the interaction between the UI and our backend server. So for the UI, we write our code in Vue.js, and for the backend, we use Python to write the code. So let's take a quick look at the UI section. We first design our page in HTML, and we also designed several dialogues so that if you click on a certain file icon, a dialog would pop up and you can do the final interactions with the UI. And if the user click on a certain button, then we're gonna call different functions so that the UI is gonna be a dynamic one. For each of the functions, each of the actual functions, how we're gonna interact, how we're gonna communicate between the front end and back end. So in the front end, we use AXIOS, and for the back end, we use Python Flask so that the information can be sent and received between those kind of servers. So now let's take a deeper look at how our backend server would manipulate our actual database. The first function would be put. This one is called when a user actually wants to put a file into our database. So this is a partition database. So the first thing we do is to allocate the file to different partitions. We use the len to get the size, and then we divided it by the preferred block size. In this case, it would be 128,000. Yeah. And so now we can get the different partition, the number of partition of the file. And then we need to allocate the blocks for the file using the allocate blocks for it, the allocate blocks function that we defined before. And we also need to create block name for each blocks, just like what we saw in the XML that we exported from the HDFS. Each block has a block number. So what we're trying to do here is to go to the inode section to find out how many files that already existed in our system. and we calculated how many block that has already been used. Used also, we add the maximum number of blocks to 1, and this become the new block number for our new file. And also getting, because we got the actual data node name by the allocate blocks, so we can actually go to the data node and get a block number and patch it to the actual block inside the data node server. And we're using the replication factor of 2 so that we need to patch it twice. Also, if we want to put a file, we also need to manipulate the name node as well. And because we're only calling the put function when we're uploading files, so we can predefine the type as file, and we just return JSON file OK to the front-end server. The second function would be make directory. So this is rather simple because we're only modifying the name node section. So we get the file name, directory name, parsing it from the front end and parsing it to the write to name node function, and predefine the type as directory and return the JSON file OK. The next one would be list. That is listing out all of the content in a directory. So to do this, we need to go to the directory section that requires the inumber of it. So first we retrieve the inumber inside the inode section, and then of course using the path parsed from the front-end server. And we try to retrieve the inumber in the directory section and append each of the child inside the directory into a list. We convert the list with the key name of data into a dictionary, JSON file it, and we return it to the front end so that the user can see the user in the front end can get the child of each directory. The next one would be removing a file. So in order to remove a file, we need to remove it from both data node and inode section, and name node section, I'm sorry. So first we get the name, and just as usual, we retrieve the inumber of the file inside the name node. And also we get the block number and the data node from the name node section, the inode section in the name node section as well. So we can directly go to the data node with the specific block number and just delete it. And also we need to delete it inside the name node section as well. But here's the tricky thing, because we need to get the parent name as well, because that's where we're going to delete it from, the directory section inside the name node. So we get the parent information using string manipulation, and we remove the entry in the directory section and remove the entry inside the inode section using the file inumber as well. And we return JSON file OK to the front end. This is it. The next function will be cat. That is to concatenate all of the file inside, all of the partition of a file inside our database. So yeah, just as usual, we retrieve the inumber inside the inode section in the name node section, and we also get the blocks information as well. And then we go to the actual data node with the blocks and concatenate the content of the file together, putting it into a string called get data. And we strip all of the extra characteristics caused by the partition process and just put it together so that the user can see what the file initially looks like. And we return it to the front end as well, so that there should be like a see content button in the front end. And the next function is remove directory. This is also rather simple because we only need to manipulate the name node. So we also like retrieve the name I-number of the directory name. We retrieve the I-number of the parent name, and we delete it in the directory section, and also delete it under the parent in the directory section as well. And also, if we want to see the content in each partition for the front end, we need to get the partition locations and read partition as well. And here's our extra functions here. What it actually does is that it goes to the inode section and just retrieve the information about data node and the block number. And this one is just the block number, and this one would actually go to the block and get the actual content inside the block to the front-end server, so that the user can click on, for example, partition 1, partition 2 to see the content in each partition. And this function is actually just when user want to upload a file inside of the front end, and the backend receive the file using this function. It has nothing to do with our actual database. So let me show you how we as users can interact with the UI. Okay, so here's our front end. You can see we're under the root. We can add a new folder to it. For example, it's called dir1, confirm, and you can see it here. After clicking on it, we actually go inside the dir1. We can add a new folder for it. For example, pre1.json. Oh, sorry. Select file, this one, and we press confirm. So what's going on underneath the hood is that the backend server is writing the file for us. Yeah, I can see it here. And if you look at the blocks, you can see that the block 0 is located at data node 2 and 3, and I have data node 3 on my machine. And okay, here is the block. Back to the front end. If we click on the file icon, you can see that here's partition 1, partition 2, and actual whole content of the file as well. We can choose to download it. Okay, and we can also delete it as well. So here, okay, the file's gone. So now I'm going to show you the next part of our presentation. That is the user interaction with the socket client and server. So here, we first create a socket server and we bind it to a port number, for example, in this case, 5555. And in the client side, we connect the client to the port number that the server has connected to. And the client side can accept user command and parsing the information to the server. After receiving the message from the client, the server would execute the functions, for example, ls, remove, and stuff like that, and send back the information to the client. The client could print the results on the terminal so that the user can get feedback. So now let me show you the actual interaction. I've already had my server running, and let's do some hands-on experiments. First, we can make a directory. We can remove the directory. Excuse me. Remove. Yeah, we remove the file. We can also like put a file inside the database, inside the dir1, for example. So what's going on right now? Still, the backend is controlling the database and writing the file for us. Great. And also we can list out the content in a certain directory. For example, this is a root, and if we type in dir1, we can see the pre1.json. We can also see the content of the file. Yeah, and we can also get the file. So now basically what I'm doing is to download the file inside my desktop. And if we switch to the desktop, you can see here pre1.json. This has just been downloaded. And the last one would be remove. And let's watch what's going on. Yeah, the file's been removed. And this is how the whole project we've been implemented. And thank you for listening. Therefore,
Yeah. 把它导出